Alright, so the last time we talked about what matter was, it's something that takes up space and has mass. Now we're going to talk about how we're going to classify matter into different categories. Alright, so matter is composed of tiny particles, and those tiny particles are atoms. And an atom is the smallest particle that will retain all the properties of that element. So if I have an element, so if I have gold, for instance, or if I have silver, if I take the tiniest particle that I can possibly take out, and that would be the atom, it would retain all the properties of the gold and of the silver. So an element is a pure substance containing one type of atom. So essentially, an element is almost the same thing as an atom. I mean, they're not the same thing, but you can kind of think about it as they are the same thing, because elements are made up of atoms, and the atoms are the smallest possible particle that you can have of an element. Alright, so we have the periodic table, and that has all of our elements on there, and they're represented by symbols. So this will probably be the most important table that you'll see in this classroom. So each element has a symbol representation. So hydrogen, for instance, is the symbol is H. So Li is the symbol for lithium, Be is a symbol for beryllium. You're not going to be required to memorize all the symbols, but you'll accidentally end up memorizing a lot of them anyway. But if you notice that a lot of the symbols, they're two letters. And it's always a capital letter followed by a lowercase letter, and this is the way you need to write them. If you write in all caps, you got to change that for this class, okay? So CS would be cesium, etc. And you can also divide the elements into three categories: metals, nonmetals, and metalloids. And if you notice, most of the elements here are metals. We only have a few metalloids, and then we only have a little bit more nonmetals. So most of the elements are metals. Alright, so matter can either be a pure substance or a mixture. So one of the types of pure substances would be elements. So they're going to be composed of identical atoms. So if copper wire, that's an element. Aluminum foil, carbon, basically anything that you can find on the periodic table. Now, a compound is also considered to be a pure substance. Okay, it is a pure substance. It's where you take two or more elements and you chemically combine them. Okay, so they are chemically combined. And they're very hard to separate. The only way that you can separate them is with a reaction, a chemical reaction. You cannot physically break them up. So it's always in a fixed ratio. And what that means is if I have a compound, so let's say that I have CO2, it's always in a fixed ratio. There is one carbon for every two oxygens. So this is the chemical formula right here. And even though you don't have a 1 by the carbon, it is 1. It's just a simply implied thing. And you will know that this is two different elements and not, for instance, like cobalt, because cobalt would be a capital C followed by a lowercase c. This is a capital C and a capital O. H2O is another chemical formula, and you will always find water in a ratio of 2 hydrogens and 1 oxygen. Okay, so the properties are going to be different from the individual elements. So even though you've got 2 or more elements in there, they will be vastly different from those elements. So if you're looking at salt, That's sodium chloride. Sodium, if I put it into water, it's very reactive. It's almost explosive in water. And then chlorine is poisonous. If I have chlorine gas, it is poisonous. Now, salt is not reactive in water, nor is it poisonous. So it has its own unique set of properties. That's what makes it a pure substance. The fact that you can't physically separate it, and it has its own unique properties. Alright, so a mixture is something where you have two or more substances and you can physically separate them. Some of it might be hard to separate, but it's possible. So if I have a mixture, all of the substances retain their properties. So when you combine sodium and chlorine together, they don't retain those properties. They have their own unique properties when they're chemically combined. Mixtures are physically combined. So if I take two or more substances and physically combine them, that is a mixture, when I'm not changing what it is. So you can either have a homogeneous or a heterogeneous mixture. A heterogeneous mixture, hetero means different, so you will actually see different types of particles. You'll see that it's not uniform. Homogeneous mixtures are uniform and they basically look like one thing. So even though if I'm looking at this particular apple juice, it looks like one thing. I know that it's got sugar, it's got water in there, it's got different things in there, but it looks very uniform. It looks like one substance. So that's a homogeneous mixture. Homo means the same, hetero means different. So a homogeneous mixture is where you have a uniform composition. So the juice that we just saw was uniform. It looks like one thing. So a homogeneous mixture is also called a solution. So if we say homogeneous mixture, you should know that it's pretty much the same thing as a solution. So solutions have very, very small particles. I can't actually see the particles that are in there. So if I dissolve sugar into water, I can't see the very, very tiny sugar molecules in there because they're so small. But they're there. They'll also have no Tyndall effect. So basically, if I take a light, I will not see the beam in the light. Okay? So basically, the light can go through it, but you don't actually see a beam being formed. And I'm going to show you a video of that in just a second where you can actually see that more clearly. So rubbing alcohol would be an example of a solution. It has water, it has alcohol in it, and it has a uniform composition. Alright, so a heterogeneous mixture, that's where you have visibly different substances. So if I have, let's say, oil and water, and I can see the oil and I can see the water, and also oil floats on the top, so definitely not going to be uniform because I can get oil in one drop and then I can get water in another drop and not get them mixed together. So when you can visibly see differences, you know it's got to be a heterogeneous mixture. Here's where it gets a little tricky. Heterogeneous mixtures can either be a colloid or it can be a suspension. Suspensions are very easy to tell. Colloids can look like they would be homogeneous. They have medium-sized particles, and they will have Tyndall effect. So you will either see the light not being able to go through the substance at all, or you will see a beam being formed. And again, I'll show you that in just a second. Right here, milk is considered a colloid. It looks like one substance. However, light will not get through it because the particles are so much bigger. Because the particles are so much bigger, we don't consider it to be homogeneous, because it actually, if you look at milk underneath a microscope, you'll see that it is heterogeneous. You'll see little bits of fat and other kinds of things that are in there. Also, the particles will not settle. So in milk, nothing ever actually settles in the milk. Whipped cream would be another example of colloid. Mayonnaise would be another example. Again, it's something, it does look like one thing, but the particles are so large the light can't get through them, or you would see a beam. Okay, suspensions are the easiest ones because the particles are very, very large and the particles will settle at the bottom. So anytime that you have to shake something up, that is a suspension. Or particles can float on the top, either way. But you will definitely see the particles being separated, which makes it heterogeneous and makes it a suspension. So fresh squeezed lemonade, where you have the bits of pulp in there and you definitely have to shake it up before you drink it, that would be a suspension. Alright, so let me Alright, so I'm going to tell you how to tell the difference between a colloid and a solution, and the easiest way to do that is Tyndall effect. So that's basically when you shine a light through it to see what happens to the light, if the light scatters or not. So you know a solution should just look like one substance, okay? It should just look like one thing. And all these things, all these appear uniform. They just look like they should be one substance. We know that they are mixtures though. So let's go ahead and look at some of these. So this one right here, this is salt water. Okay, so I'm going to take this laser and I'm going to shine it into the solution, or into this cup. And if you look right there, you don't see the beam of light. It does go through it, because it's going on my Cheerios right now, but you do not see the actual beam of light. That's because the particles are so small it can't scatter the light and actually form that beam. So that is no Tyndall effect. This is a solution. So let's look at this one. Okay, this is the flat soda. Okay, again, I'm going to put it through that. Okay, you do see lasers, but you don't see the actual beam of light. It's still going through it. Okay, but you don't see the beam of light. The light is not being scattered. So again, that's no Tyndall effect. So notice also that this is not a colorless solution. Solutions can be more than clear. They can have color to them. Alright, let's look at this one. This is milk. I'm going to put my laser up against it. And it does not go through the milk. Okay? This is a colloid in which the particles are so large that light will not go through it. So this cannot be a solution because the particles are so large, light cannot travel through it. Let's take a look at a different one. This one's a little bit harder. This is the juice I was talking about. Now, some juices will not behave this way. Okay, so let's look. Oh, you see the beam right there. It's forming. It's not going all the way through, but it is forming because the particles are large enough that you can actually scatter the light. So this is Tyndall effect right here. This is not a solution. Let's go through some examples. If I have these mixtures and I want to know if they are a colloid, suspension, or a solution, I'm going to reason my way through this. So mayonnaise right here, it does look like it could be one substance, but you know the particles are very, very large, so it is considered to be a colloid. Okay, muddy water, if you think about the dirt, it's going to eventually settle at the bottom, which makes it a suspension. Alright, fog. Fog, if you think about it, it does look like it could be one substance. However, if you take a light and shine it through it, you can actually see the beam of light, which makes it a colloid. It has Tyndall effect. Now salt water, if I take salt and I dissolve it into water, what actually ends up happening is the particles of salt will separate themselves, so they're so tiny you cannot see them. And it looks very uniform, so that would make it a solution. All right, Italian salad dressing. Got to shake it up, so that makes it a suspension. Okay, so if I'm just thinking about different types of matter, so I can have a pure substance, which can either be an element, it could be a compound, these are both pure substances, remember, have their own unique properties. You can't chemically separate them, or you can't physically separate them. And then if you are not an element or a compound, so you're not pure, you're going to be a mixture. And if you're a mixture, you can either be homo or you can be hetero. Geneous, homogeneous, okay. So graphite is just carbon. So the stuff that you have in your pencils, it's just made with carbon. So that is just an element. So if it's something, just one thing that you can find on the periodic table, it's an element. Pepper, if you look at pepper, you can visibly see the different substances in there, and it's definitely made with more than one pure substance. So it is a heterogeneous mixture. All right, sugar. Sugar is made with carbon, hydrogen, and oxygen. So this is something that's chemically combined. It is a compound. You cannot physically separate the carbon from the hydrogen from the oxygen. They are chemically combined. The only way to separate them is by chemical means, with a chemical change. All right, paint. Paint is a heterogeneous mixture. The particles are very, very large in the paint, so that would make it hetero. And then soda. Soda would be a solution. All right, so that concludes this podcast. So